Now we know how the consensus is reached, of how something has happened. The next thing we have to decide and we have to talk about is the form of immutability. So that means that information of the past cannot be changed. Now first, let me repeat again that the assumption is that you cannot fake a signature, right? So I will discuss that in much detail in the decentralized finance class of why that's not possible, or why it's not possible in polynomial time is the precise description. But there is a question of the immutability of records. So can you change a record in the past? Now how would you actually do that? So now here what you see is you see all these blockchains, right? These blocks that all refer to one another. And I said before that if you want to change one of these blocks, all of the reference points from the new blocks would be faulty, and the network would reject these. So that sounds like this is secure, while it is not entirely. Because let's say this first block here contains this transaction from Bob to Alice, and let's say Bob wants to mitigate it, eliminate it, change the quantity, whatever he wants to do. He basically wants to fake it. So you know that already if you put that information in, the network as a whole would reject it. However, one way how you could get this done is if all of these blocks that you have here, if you ignore them and rewrite history. So you basically create a whole new alternative reality where the transaction that happened in the block that you want to eliminate or that you want to fake is no longer there. So how can this be done? Well, it could be done by basically just recreating all of these blocks by taking the digest, however, relating to the fake block that you want. Now, is this something you can do? And the answer is no. This is, well, not conceivably. So here's the idea of how this would work. So normally when you have, so first of all, we have to talk about something referred to as the longest chain incentive. So now how does this work? Suppose you have, an existing blockchain, and then you have two blocks that are created essentially roughly at the same time. This can always happen. And now let's say as another block is, so when the two blocks have been created at the same time, a new miner wants to create a new block, has the decision to take of which of these two blocks to go to. Now suppose that miner attaches it to the lower part of the chain. And suppose somebody else attaches it to the lower part of the chain. So the first thing we have to understand is when the next miner comes, the seventh miner, where would this miner put the information? Which block would this miner relate to? Well, let's just think about this intuitively. The way it works is that as a miner, you receive money for transactions that you have processed. So you receive fees and you receive a block reward. Now, if you happen to be creating a block that nobody else wants to reference to, then nobody will also accept the fact that you have actually a legitimate claim on the block reward. So whatever work you have put in has just gone to waste. So the miner who creates a new block, the block number 7, wants to attach it to the block 6 because it is more likely that people will go with the longest chain, right? All right, so for that end, any miner who comes would want to attach a new block to the longest piece of the chain. Otherwise, they would lose whatever effort they have put in. Now, if you want to alter the past, going back to that problem, here in the second block here, what a new miner has to do, the new miner has to create this new reality, right? So basically has to create all of these new blocks, while other people want to attach blocks to the other chain. So in order to eliminate that transaction at the beginning, the new reality has to be sufficiently long so that the network as a whole actually wants to attach to your new reality. Now, how can you do this? Well, you have to create these blocks at really high rate, which means that you need a lot of processing power, because otherwise creating a block in and by itself is very costly. So how would you do this? Right? So what you need to do is you need to do a lot of transactions. You need to do a lot of processing of information. So what you need to be able is you need to be predictably able to create a new block. And you need to be faster, therefore, or you need to be faster than everybody else. So what you really need is you need to have the ability to create new blocks and or to be able to reject what everybody else has been doing so that you can break this Byzantine protocol where everybody agrees on something that happens. So the way to do this is you need to, and this is referred to as the 51% attack. The most basic way how you can do this is if you have more than 51% of the processing power, then you can basically reject any new block that would be added to the longer chain, and you can create, the new blocks in your own time. Now I have some numbers here which are a little dated, but just to give you the picture of how this works. So this is, I think, data even from 2018 or so. Hang on with this because it just, the numbers get just more astronomical as we go into 2020. So currently the network has a combined power of 25 million terahashes per second, which means basically the number of guesses that they can make per second. Okay, so at that hash rate, the best GPUs, so that's the graphical user chips that create these hashes, can do about 0.025 terahashes per second. So you need about 25 million of these graphics cards to have, and they so that you have a total of the GPU power of 5 billion GPUs. So now one GPU costs about $200. So basically what you need is, and you see the number as it is there, is something of $1 trillion. Is it $1 trillion? Yeah, I think it is over $1 trillion that you need to invest in order to crack the network and to have enough money to have 51% of the processing power. As you can see, this is clearly a lot. Now, I have tried to convince you that this is something which is really difficult to do, right? So it requires an enormous amount of money to get the 51%. However, you need to think about this problem. You need to think this problem through, right? So the idea of a double spending attack is you can steal something from the blockchain, right? So you can reverse a transaction. You can spend the same money twice. Now, if you think about what I described just now of how you would do a double spending attack, is as follows: is what you have created an alternative reality. Now, I told you it's extremely expensive to do, but let's just take a step back. And not all, so what I basically did as an example for the hashing power, I took the Bitcoin network. But there's many other blockchains that all purport to have some way of you being able to use a blockchain for the transfer of value, and not all of them are secured by the same amount of technology, if you want, as the Bitcoin network. So very abstractly speaking, when you have this kind of network where you create these blocks, as you create your alternative reality, there's actually something else that happens, because as you create the alternative reality, you actually pay yourself the block reward or whatever the fees are. So you're actually gaining money. So in other words, what you would do is, by making this double spending attack, and if it is successful, or when it is successful, is you stole what you were planning on stealing, plus you have rewarded yourself with all of the rewards that come from creating the blockchain. So now if you take that problem together, and think about it mainly as an economist, the basic idea of a competitive equilibrium here has to be this. It's like the aggregate mining cost that you have has to be equal to the aggregate mining reward. And so when you have your double spending attack, where you need to create an alternative reality of length n, then you will also receive the block rewards. So that raises the question of how big do these block rewards have to be in order to make this chain secure. Meaning, why am I saying this? Well, I'm saying this is the rest of the possible miners have to have the willingness to invest in the mining technology, so precisely to prevent these double spending attacks. And there's a very clever paper by Jonathan Chiu and Torsten Köppel, published in the Review of Financial Studies in 2018, that puts a formula to this. And it says basically, in order for the blockchain to be secure, what has to happen is that the mining reward multiplied with a particular consensus, common sense length of the chain when you consider it secure, has to be larger than the amount of the bubble spending. Now, what do I mean with that? It means that if you can steal, say, a house on the blockchain, which could be several $million, then you either need to wait for a very long time you need to be willing to wait for a very long time for the transaction to be considered final, or you need to pay miners a very large mining reward for them to secure the blockchain. And if you think of the current world of Bitcoin, for instance, the mining reward is not small. It's on the order of, let's say, $10,000. And the number of transactions that people think about that it takes for something to be secure is roughly 10 new blocks. So it's an hour, right? Because a new block there gets created every 10 minutes. So roughly speaking, right? So you have 10,000 times 10 times 11, right? So that's roughly $1 million, right? Roughly $1 million worth of, but at the given rate is what you can secure on the blockchain. Now, if you put a house as a tokenized asset on the Bitcoin blockchain, you can immediately see a house that is worth several $1 million is not enough. So irrespective of how much the technology costs would be in order to get the 51% attack, the intrinsic economics of the blockchain are not sufficient to sustain very large amounts to be secured there. So keep that in mind.